Hey, good afternoon, everyone. Thank you so much for joining us today for our wonderful methods workshop series. We are just so delighted today to have Dr. Jean Powell here with us to share about her exciting work and demonstrate the application of NLP for health research. But before I turn it over to her, I just want to give a little bit of background about Dr. Powell. She earned her PhD in neuroscience and animal behavior from Emory University just recently, 2024. Congratulations. And her dissertation was titled Text as Data, Leveraging Natural Language Processing to Decode Parkinson's Disease. It's laid the foundation for her current interdisciplinary work at the intersection of neurology, machine learning, and patient-centered research. Dr. Powell is currently a postdoctoral fellow in the Department of Biomedical Informatics at Emory University School of Medicine, where she works jointly with the CFAR Laboratory and the Motion Analysis Laboratory. Her research integrates neuroscience, biomedical informatics, and artificial intelligence with a focus on applying natural language processing, or NLP, to research neurodegenerative diseases. She develops methods to extract clinically meaningful information from a variety of sources, including social media, clinical notes, and patient-reported outcomes, with the goal of improving a digital phenotyping and advancing equitable care in movement disorders. So thank you so much, Dr. Powell, for making the time to provide this workshop to us today. And I'll turn the floor over to you now.
Great. Thank you so much for that introduction. I'm really happy to be here today and share some of my work and the techniques I use. Um, a little bit more about me, I guess, that I wanted to share is my PhD is in neuroscience and animal behavior. I do not identify as a computer scientist. I've learned these techniques along the way, due in no small part to my firm belief that natural language processing has a really powerful role in research, even if nothing else, because we as scientists exchange our ideas in writing. So natural language processing can really help us stay on the forefront of the literature in addition to performing our actual research. Um, but before we get started, I did want to start by just polling the audience so I have a little better sense of who you all are. Um, I guess I would love it if everyone could raise their hand if, and I guess I'll start with the negative because it's more informative, if you have never used Python before. Okay, we've got a lot of people. Um, Please do not hesitate to interrupt. When I got involved in this field, one of the most overwhelming things, to me at least, was the jargon. It's a lot of new terminology. I'll try to make analogies when possible, because I don't think it's as scary as the jargon makes it sound. And especially in this day and age with ChatGPT, you can explain your research problem and what you hope to accomplish with natural language processing to ChatGPT, and it can write the Python for you and explain line by line what it's doing as a sanity check. So the barrier to entry with Python is lower. There will be a portion where I show what executing this code will look like. So hopefully we can get through that together. My next question is raise your hand if you've never engaged with natural language processing, and this includes even talking to ChatGPT. Okay, significantly less hands. So we are familiar with the power that is ChatGPT. It's definitely my favorite tool, but as we'll cover, not HIPAA compliant. So with that, today I hope to provide you with a high-level overview of natural language processing as a field, as a toolbox, and how you measure performance. It's a little different than your standard t-tests that come up in more traditional research settings. What it means to apply natural language processing to health research, specifically considering how to get your research study past IRB review. And then I will have two case studies that go into more depth of how to execute these pipelines in my own research. The first one being a binary classification task using classical machine learning. So there's that jargon. The second one being a multi-class classification project using large language models. And then I'll do a really quick wrap up, and hopefully we have tons of times for questions for all of you, if you have any. So natural language processing as a field sits at the intersection of computer science and linguistics. Um, at its core, the purpose of these techniques is to get computers to process human language, and nowadays also often generate human language. And to do so requires linguistic research as well. Like, how do we get a computer to recognize an adjective versus a noun, even? And the tools and techniques used in this field also sit in the AI machine learning box, where some tools and techniques, such as logistic regression, can come up across modalities, including basic research when you're trying to predict a binary category. And large language models have become mainstream because of, no, excuse me, large language models have made natural language processing mainstream, like ChatGPT, but the field is much older than that. So in the 1950s, natural language processing as a field really hit the scene with what are called rule-based algorithms. And these algorithms are where you tell the computer exactly what you want it to do. In this case, it was translating Russian text into English, and it was done by creating a dictionary that directly mapped a Russian term onto an English term. These rule-based algorithms are quick, computationally inexpensive, extremely explainable, extremely interpretable, but also quite brittle. If the rule is not in the dictionary, it will not be applied, and it's not robust to things like typos. In the 1990s, statistical methods emerged. These methods looked at documents and interpreted them almost as a bag of their words. The order of the words didn't matter, but the assumption was the words that make up a document hold meaning and have patterns. And these are techniques that are still used today because it's true. For example, let's say you're looking to determine whether or not patients are smokers. One first pass might be to look for documents that contain words related to smoking because you don't need to spend time looking at documents that don't. And unlike rule-based, where you'd have to define every single way smoking might come up as a term, nicotine, tobacco, vaping, these statistical methods are more robust and can expand the vocabulary to identify those documents. However, they do not take into account the context in which the word is found. So in 2013, embedding models emerged, and these embedding models were able to learn the relationships between words based on the words that they are found around and synonyms too. So if a word is found in the same context as another word, its mathematical relationship will be quite close. And you can think of these embeddings almost like your SAT analogies. King is to queen as boy is to girl. And so through these techniques, we were able to represent those analogies. However, it still didn't really take into account the exact context in your own document that that word is found. It still couldn't take into account things like negation. And that's when and so in 2017, everything changed with transformers. Transformers are why we are where we are today. There's a seminal paper called Attention is All You That You Need. From a beginner perspective, I don't necessarily recommend it. It's quite dense. It's presenting this architecture and targeted towards a computer science audience. But it's titled Attention is All You Need because these transformers have this multi-head attention mechanism that can pretty much sit at a sentence, look both ways, and take into account the context in which you're providing it information. And in doing so, it can take into account negations, synonyms, typos, and it's quite robust. And now today we're in the era of large language models, and these large language models are actually built on top of transformers. What differentiates them from when you refer to a transformer alone is they've been trained on like the entire internet, and that's why they're called large language models. So this progression is a progression really like from simplicity to complexity. It's also a progression from computationally inexpensive to computationally expensive. Um, Also, as it gets more complex, it gets less explainable, less interpretable. And so, even though large language models are the most powerful tool we have in our arsenal right now, sometimes the correct tool for your research problem is on the simpler side of the spectrum. So, for example, very recently, I've been involved in a problem where we're looking to remove PHI from a data set. Um, and the data were collected in specific study sites. So it's a very easy, robust, and explainable first pass on the data to remove the study site names, the geography that we know will be in the data. We don't need anything fancy to know that this town name will be there. We can just remove it. And also, regardless of these complexities, at the end of the day, all natural language processing boils down to representing text in some mathematical way. And that also contributes to why it goes from more to less explainable because those large language models are so massive. It's really, and also now proprietary and opaque. It's really hard to know exactly what's mathematically going on under the hood. When you are doing machine learning in general, which encompasses natural language processing, you have two approaches you can use, supervised learning or unsupervised learning. And when, in addition to picking your tool, you also need to pick your approach. So supervised learning is when you have labeled data that guides the model. So for example, you might want to predict patient outcomes from health records when you already know the patient outcomes. It's more of like a retrospective look. And in unsupervised techniques, the model finds patterns on its own. So, for example, you might do topic modeling on patient notes. Both of these approaches have their own spaces in research. It's, you know, developing a model you want to deploy on future clinical data, usually a supervised approach. You want to, because supervised approaches also allow you to extensively validate the model because you have what's called a ground truth data set. So you know what the right answer was and you know whether the model came to that right answer. But unsupervised techniques are very exploratory and could provide insights into avenues that you wouldn't have necessarily pre-labeled yourself. And then in the field of natural language processing, there are what are called multiple tasks. You might have a problem, and there are multiple ways that you could frame that problem. And different models have been designed around solving different types of problems. So, one such problem is named entity recognition, where you identify and categorize chunks of text into predefined categories. So, an example would be flagging mentions of drug names. And to take that a step further, you might do information extraction where you're pulling structured text from unstructured text. And so you might want to know Advil is mentioned. Advil is a drug, and that's why we're identifying it. So we're getting the drug name and we're getting its dosage all at once. And this could be the difference between like broad surveillance and like a specific research question to go from named entity recognition to information extraction. You can also summarize. You can condense long text into digestible summaries. I'll get into this later. One of my current projects I'll be presenting is generating history of present illness statements from transcripts. And there's also what's called classification, where you're categorizing text into different groups. This is my favorite one. I think it's very explainable and it's also very, like you can check it really easily because you can do a lot of classification projects with a clearly labeled data set, and you have a very clear cut idea of how your model is performing. Um, so, with that, with performance, machine learning models are measured by comparing the ground truth label that expert annotators have created to the predicted class from the machine learning model. And it falls into what this box, which is called a confusion matrix. And so on the left, we have the ground truth classes. In this case, it's positive and negative. These names don't really matter. It can be class A, class B, and you can also have even multi-class problems where there are three, four, or five options. And you have the predicted class with the model, which is also the same classes as the ground truth. If the class is positive, the model predicts positive, that's a true positive. If the class is negative, the model predicts negative, that's a true negative. And those are accurate predictions from the model. If you get a false positive or a false negative, the model made the wrong prediction. And the relative importance of these false positives and false negatives really depend on your research question. And there are these predefined metrics that come up all the time, especially in clinical spaces. You're often looking at precision, sensitivity slash recall, and F1 score, because these metrics take into account false positives and false negatives in different ways. So, take, for example, our recent COVID-19 experiences. If your goal is to make sure that everyone who has COVID knows they have COVID and quarantines, you probably want to develop a test that has high sensitivity or recall, where all true positives are captured, very few false negatives occur, and you don't care if a lot of people who don't have COVID think they have COVID because they're staying out of public, and that's the public health goal. Counterpoint, if it's a resource intensive problem, let's stick with COVID, you only have 10 hotel rooms. You might want to optimize precision where everyone who is told they have COVID does have COVID. You don't have false positives because the resources need to be allocated to true cases. And so your research question really dictates which of these performance metrics matter to you. And then the F1 score is the harmonic mean between precision and recall. So if both are kind of equally important, people usually default to an F1 score. Um, there is accuracy as well here, but if you have an unbalanced data set, which means one class has a lot more examples than other classes, accuracy can be really skewed. So if 98% of your sample is a positive class, the model can learn always say positive 100% of the time. The model becomes 98% accurate. However, it ends up having 0% accuracy for the negative class. And so precision, recall, and F1 score take into account that it is not performing equally across all classes. And there's further subsetting of this math. It's called micro and macro scores, where micro assumes your data set is balanced and macro assumes it's not. And because it's not, it will give more weight to the minority class. So if it's the model is really struggling in the minority class, and that's reflected in the performance metrics. And I know this is a lot of jargon, a lot to wrap your head around, but it's really important for assessing your model's performance and like when to stop experimenting as well. And unfortunately, there's really no score that you want to aim for. Like, obviously, everyone aims for perfection. You would love if every score was 1 or 100%. Sometimes that's not viable. Sometimes the publication is, we've been experimenting for months and we achieve zero point 0.5 F1 score. And that's still publishable. The clinical takeaway might be we're making leaps and bounds, but it's like not ready for clinical deployment. And this came up recently in my group where our previous paper, the F1 score was 0.2, and our new experimentation got us up to 0.5. So it's like drastic improvement. We're like chipping away at this problem, but the problem is not clinically ready. So now natural language processing in health research specifically. Number one, privacy and compliance. That is the most important thing when deciding on how to conduct this research. You have to consider HIPAA and PHI restrictions. You have to get approval both from the IRB and also the Office of Information Technology. And I cannot stress this enough. You cannot use ChatGPT to process identifiable data. You also probably should not put unidentifiable data into ChatGPT. There's some like data ownership issues as well. They're not a transparent company. Never give your data to them. Ask them to write code for you all day, every day. Do not give them your data sets. And to say more about the approval process, to get NLP research approved, you go through the standard IRB review. And also, I do realize some people in the audience aren't from Emory. I am speaking from my specific experience at Emory. Your institution might be a little different. When you're filling out the IRB, they will ask in our new insight system, there's even a button for it, like, will you be using these approaches? And if you say yes, you require additional approval from the Office of Information Technology before the IRB will review your stuff. And OIT will make a ruling about whether or not you are, um, performing safe research using these approaches. And the real key question is, will the data ever leave Emory? If all approaches you're doing can be executed on your local laptop off of Wi-Fi, you are imposing as much danger as running a t-test. It's really negligible. It's a new way to analyze data. But if you're trying to use a very advanced technique, even the lesser transformer models, not even the large language models, sometimes require access to cloud compute and GPUs, because they're really computationally expensive and you can no longer run them locally on your machine. So to maintain data safety, you either need access to a local HIPAA compliant cluster, and that's another point. Not all local clusters are HIPAA compliant. I'm very blessed in the Department of Biomedical Informatics that our cluster is HIPAA compliant. Um, and if you do not have access to that HIPAA compliant cluster, you have to get access to HIPAA compliant cloud computing. And at Emory, we have a partnership with AWS, Amazon Web Services, where you can pay for HIPAA compliant cloud compute. It's at cost, but it is feasible to use large language models in a HIPAA compliant way here at Emory. So all in all, you're required a data protection plan. And even if you're using HIPAA compliant cloud compute or a HIPAA compliant cluster, they want to make sure you've thought about everything that matters when dealing with clinical data. Next, costs and resources. Large language models are extremely expensive to run. Even on my local cluster, this isn't a cost that myself or my lab directly needs to pay, but every time I query a large language model on our cluster, it can take like a minute per query. So if you want to run 1,000 texts through it, that's 1,000 minutes. That is resources that I am monopolizing against the entire department. And then that's also just my own resources of, is this project feasible? Because it's going to take however long to run. Again, cloud services exist but they come at an additional cost. And if you do have access to a HIPAA compliant compute cluster, it does come at a lower cost. I can only speak from my experience in BMI. You do have to kind of luck out. So our collaborators who are outside of our department are not allowed access to our compute cluster. And that's where collaboration comes in. People approach us and we become collaborators on the project and we can execute the code. But it all depends on which department and which institutional infrastructure you fall into. And then lastly, interpretability and trust. Clinical collaborators need explainable outputs to trust the model that they're using. And there are trade-offs, the power of a large language model versus the interpretability of a rule-based method. Because at the end of the day, they need to trust that if something is getting clinically deployed, it's up to clinical standards. And reproducibility and evaluation are really non-negotiable. We are not at a stage, even with large language models right now, in my opinion, where you can just throw a problem at it without doing any vetting and evaluation of its performance. So I'm about to segue into the case studies. So I will pause for a second. Are there any questions? Okay. So the first case study is using binary classification and classical machine learning models, specifically supervised learning and statistical methods. I hope these words are a little bit more known to you now. And this work has been co-advised by Doctors McKay and Sarker, and the data set itself was actually acquired by Dr. McKay. So a little background on the project. Falls are really heterogeneous and can result from multiple types of biomechanical perturbations. You can fall because your foot got stuck on something and you continue propelling forward, and that's a base of support fall. But you can also fall just because you kind of lost control of your balance, which is a center of mass fall. And in research, falls are almost always aggregated into one category, and this is due in part to the fact that the resources required to manually adjudicate every fall in a data set, which could be thousands of falls, is too much. But it's super important to do because in disorders like Parkinson's disease, as the disease progresses, a person might experience more center of mass falls, and also the intervention to prevent falls might be different depending on what's causing the fall. If you're constantly tripping over your rug, it's like a really easy fix to remove that rug from your home. If you're experiencing a lot of center of mass falls, the solutions sometimes are like you cannot ambulate and talk at the same time because maintaining your balance control requires that much of your attention. So here's a high level overview of our methods where we were looking to develop this as a natural language processing problem. We had a data set of fall records. So like was walking into the bathroom and slipped, landed on the left knee, elbow, and pulled self up. So the problem is how can we take that and get a computer to predict the biomechanical cause of that fall? And the first step is converting the text into numbers so that the computer can read it. And when using statistical approaches, those numbers look something like this, where you have a data frame, and each row in the data frame is one fall event or one document. And also, just from another jargon perspective, I might let this slip later. The term corpus means all the documents in your data set. So each row is a document, and each column is a word that is found in your data set. And then in each cell, I just did black and white, but you can have a variety of values, whether that's a binary, the word is present or not in the document, or the count of the times that those words come up in the document. You can also add what are called other features to the model that could go beyond text. In this particular project, I had the age of the participant and the duration of time that they had Parkinson's disease. And then in a supervised approach, you have your class label. In a binary classification problem, that'll be two values that is associated with every document. And then you train a model to predict which class the data fall into. So this is a representation of what might be output from a support vector machine, where the model learns to draw a boundary in n-dimensional space of the data, and all data points that fall on one side of the boundary fall into class 1, and all data points that fall on the other side of the boundary fall into class 2. And I made it a point here to have incorrect data points on the wrong side because these models aren't perfect. Even with the training data, you might not get anywhere near high accuracy. And that's a reflection of many things. It could be the reflection of the quality of the pre-processing, which we'll get into. It could be a reflection of having too small of a sample size. It could also mean you weren't using the most appropriate model for your data set. So there are many factors you have to consider. But when the model is trained, when you have new unseen data, it will classify it as class 2 because that data point falls on that side of the predefined boundary from the training data. So that's a very high level overview, but now buckle your seatbelt because we're about to deep dive into it. In this particular project, I had 3 types of data: raw fall descriptions, raw fall location descriptions, which is also text data, and structured patient information. And in order to give that information to the model, there's a lot of pre-processing that has to occur. So first, I did manual spell check because it was just a small enough data set that I could do that. And again, here's that example of slipping in the bathroom. And then I lowercased all of the words and I removed punctuation. And so the text is transformed into this. I then apply what's called the Porter stemmer. The Porter stemmer is a specific tool, but the point of stemming is it takes the root of the word. So if you have different conjugations, walking, walked, walks, it'll all break down into walk. And so it will be able to treat different conjugations of the same word as the same word. And that's really important because it can reduce the dimensionality of your data. Text data sets are really wide. There are so many unique words in the data set, and these models can only handle so much wideness, especially if you don't have very many examples. So dimensionality reduction techniques are really important here. And stemming is one way you can reduce dimensionality without losing too much meaning. There's also this process called lemmatization, where instead of going to the root of the word, it like does a complete word. And it usually has better results, but it's more computationally expensive. So it also depends on the size of your data set. And then lastly, I removed stop words. So stop words are filler words that carry no semantic weight, like the, and. And so that's another dimensionality reduction technique where you remove noise, and it often improves the performance of the model. But it also depends. So if this were a sentiment analysis research question where, and this is the live coding example where we're looking at positive and negative reviews, sometimes punctuation and capitalization matter. An exclamation point in a review might be indicative of a positive review because someone's enthusiastic. So it really depends on your data and your problem at hand, what pre-processing steps occur. For other types of data, in this case, I just manually binarized the location as at home or not at home. And then you have to do what's called one-hot encoding, where it separates those options into two columns so the model can handle it like they do the individual words. And for structured patient information, if it is a categorical variable, also do one-hot encoding. But if it is a numerical variable, you also have to do what's called standard scaling, because most of the text data and the categorical data will be zeros and ones. So if you have a numerical value that is much larger than that, even age ranges where we had people in their 80s in this study, that's a really big number that can really pull the model away, even though the individual feature isn't that important. So when you scale numerical values, it puts them between 0 and 1. So it matches the scale of the binary variables. So once it was pre-processed, I was able to do model feature selection and then start training. When you do these types of things, you put 80% of your data, usually you can alter the percentage, into your training set because you do not want any test data leaked. When you're assessing the quality of the model, you want it to be unseen data so you know how your models generalize. And in this particular example, I trained on a lot of models, and including an ensemble model, which is a combination of multiple models, and it'll adjudicate a decision. And then I evaluated the trained model's performance using F1 macro score on the 20% of data. Again, macro because I had an unbalanced data set. And overall, model performance was good. It had an F1 macro score of 0.89, but a very wide confidence interval. And part of why it was so wide is ultimately 20% of my data was only 25 training examples. But it predicted 18 center of mass falls as center of mass, 5 other as other, and it miscalculated or mislabeled 2 other class falls as center of mass falls. So you might be sitting here wondering, how do you actually execute this? And I think the code is simultaneously easier than you expect, and if you have never used Python, probably still intimidating, so I apologize on that. But I created a Colab notebook to share with you all. I'm going to put it in the chat to just walk you through what executing something like this might look like. And let me change my screen share. And you should have view access. You do not have editing access, but you are more than welcome to copy this code into your own endeavors. So this is a Jupyter notebook. I really like it because you can have individual cells that you can execute on an individual level instead of running your entire pipeline at once. And a really great tool when you're just getting started in natural language processing, especially if you don't have access to institutional resources, is Google Colab, because you can, with an EDU address, actually get a lot of access to a lot of free monthly compute power. I have a high school student who works on Reddit data with me. So Reddit data does not contain PHI or any identifiable. It can have identifiable information, but it's not protected. And so he can access it and he can run it on Google Colab. And he's even been able to train a large language or query a large language model using Google Colab for free. So I'm going to go very quickly through this for the sake of time, but I am going to just run everything below this cell if I can do that. Maybe not. Um, okay. Am I in the right Google? Oh, that's fine. Okay, now I'm in my right Google where I own it. So this first cell installs dependent libraries. When you code, you can think of Python as a workshop where you're trying to complete a project and you have your local environment. Consider yourself in an empty room and you want to bring tools into your environment. Maybe you need a table saw, maybe you need a jigsaw, but you also don't want every tool all the time being in your environment because then you're unable to move and things get in the way. So first you install your dependent libraries into your environment and you're able to do that with that exclamation point before the line. And then you have to move those libraries in. So those are these import statements. I've already downloaded all of this, so this will hopefully move fast. It's just connecting. And then we have some resources. So when I say remove stop words and remove punctuation and stem words, these are pre-existing toolkits that are available to you. And so in one line of code, you're able to load in something that you can just deploy. It's not like you need to hard code what a stop word is yourself in this day and age. And then in this particular example, I've loaded a movie review data set. I'm not going to press play at this time because it takes quite a while. But you can play around with free data sets like this, and it's a great learning opportunity, especially when you're using something that like isn't HIPAA compliant, so you don't want to put your own data in quite yet. And then I defined a lot of pre-processing functions that will load the data and clean the data in the way I described in my previous slides, and an experimental run that will train a k-nearest neighbor classifier on the data. A k-nearest neighbor classifier, oh, things not, oh, base dir was not defined. Well, I did need to run this cell. Well, I do need to re-download this at this time. So a k-nearest neighbor algorithm will plot your data in n-dimensional space, and then the nearest neighbor comes in where once it's come up with the modeling, when you put new data in, it will assign the class of like whatever data point is closest to your old training data. And you can define the number of neighbors that matter. That could be 5 neighbors, that could be 10 neighbors, that could be 50 neighbors. And when you're selecting models, not only do you select them for how they divide the data, you also have to do what's called hyperparameter tuning, where you determine the optimal, for in this example, number of neighbors needed to optimize your model based on your unique training data. And in this example, I'm now training the model using multiple pre-processing steps where I keep adding other ways to change the data. And for the sake of time, I am just going to go down to the summary table where there was no change in performance from raw text to lowercasing, and that's because some of the toolkits currently in the library automatically lowercase everything. When I add stemming, improvement F1 score actually doesn't really change much. But and also when I add stop words, it's negligible in performance improvement. So when you see things like this, that might mean that it's not worth the compute if this is a really slow process. But when I remove punctuation, performance increases pretty drastically. It's up to 0.71. And when I do a statistical technique called TF-IDF, which is term frequency inverse document frequency, which takes into account the popularity of a term in a given document against the popularity of the term in the entire corpus. So it really hones in on the most important words and drastically reduces the dimensionality of the problem. Performance goes up again to 0.73. And so when you experiment like this, you need to experiment as well with these pre-processing steps. It's not one size fits all. The models are not one size fits all. And when you're using classical approaches, most of your time goes into these pre-processing steps. Um, so that was very fast. I will pause again for questions. Okay, let me share my PowerPoint again. So my next case study, which is what you all might be waiting for, is large language models. So doing multi-class classification, which means there's more than two options using a large language model. It's a supervised learning task again, and it's built on transformer-based large language models. Um, and shout out to Dr. Brydup. He is the project lead and the mastermind behind all of this. So for some background, dementia is an umbrella term. It encompasses multiple diseases. It affects millions of people, and early detection is really difficult because primary care providers aren't very comfortable with recognizing and diagnosing dementias, and neurologists are swamped already. So as a result, the people with the most severe dementias, which I'm representing by question mark signs, get funneled to the neurologist pretty effectively, where people with more mild cognitive impairment generally have to kind of wait their turn to get to see that specialist, even though early diagnosis is so important for prognosis and for autonomous decision making before the dementia is too advanced. So this project was built around the idea that if automated tools could reliably summarize symptoms into a structured history of present illness statement, we could reduce clinical workload and improve clinical care access. So this is a two-step project. One, we've developed a chatbot that interviews patients, so a clinician doesn't need to be in the loop and they can be assessed efficiently. And the next step, which is where I'm involved, is to develop and evaluate large language model based methods to label the status of a symptom based on the clinical transcripts. So we framed this as a supervised multi-class classification problem where we have these transcripts. We have predefined symptom types and symptom definitions. So for example, language problems could be defined as word finding difficulties, comprehension problems, pronunciation difficulties, and slurred speech. And we want to determine, based on the transcript for that patient, whether that symptom is present, absent, they've had a past history of the symptom, it's ambiguous whether they have the symptom, the chatbot asked or the clinician asked, but the patient did not provide information, or the symptom never came up at all in the transcript. And we've got about 40 or so symptoms we're experimenting with. And first, we've developed what the ground truth data set. We've been labeling these data manually with at least two annotators, and then we come together and adjudicate disagreements to get that gold standard data. And now we're trying to get the large language model to do the same. And methodologically, this is extremely different. In some ways simpler, in other ways quirkier than traditional approaches, where instead of feature engineering, we're now prompt engineering. And you don't retrain models like you do in classical approaches. You design prompts that guide the model. And this is also why large language models are really black boxes. You cannot really impact the underlying relationships between words. You don't necessarily know what it was trained on. You don't necessarily know what it knows or why it knows it or why it came to a decision. And you can have two types of prompts. Zero shot, which is no examples. Does this person experience language problems? Or few shot prompts. Does this person experience language problems? And a language problem could look like XYZ. It does not look like XYZ. That further gives context to the model of what they might be looking for. It's extremely computationally expensive. It's time consuming. It can be costly if you don't have access to a large language model. And there are HIPAA constraints. Again, it has to go through HIPAA compliant channels to give your data to these models. And then there are challenges. Again, the models have quirks. They're very sensitive to syntax and formatting. For this particular experiment, I'm experimenting with GPT OSS 120 billion, which is the GPT family model that they've made available to host locally on computing clusters. And for it to work at all, I have to start every single prompt with this start system message, reasoning, conservative clinical inference. In this detail section is when I actually describe what symptom they're looking for. And then I have to give it the output schema. I want it output as a JSON file so that I can parse it as structured data and assess if the label is correct. And restart a new message, insert the clinical transcript, end again, and then start the model's own response with JSON nomenclature because it will finish the JSON. But if I don't do this, it will write me paragraphs and paragraphs about why it came to its decision. And the final bit might be the decision in a structured way, but it's hidden in these paragraphs and paragraphs of text. Um, so when you use a large language model to perform classification, it isn't plug and play. Um, you need your supervised data set, which can be really time consuming to get. You have to combine prompt engineering with experimental runs. I really recommend MLflow as a tool where every time you run it, it will track the prompt you used, the weights you used for the model, and the model output. So if things change, you can like revert back to a higher performing thing without needing to keep your own lab notebook, so to speak, or rewriting your code over and over again for every change you make. And you have to optimize, and in our case, we're optimizing both fine grain labels and binary labels because we're aiming for clinical utility. And here in this figure, I have runs I've done on the model for activities of daily living as a symptom. And you can see my first couple of experiments had extremely low performance. This is the F1 score. And I will fully admit on record, on recording, this occurred because I didn't accurately put the transcript into the prompt. This does require, Python to insert things where they need to be. And I'm like, why is this going wrong? I'm running it again and again. Everything is getting labeled as not discussed. And it's not discussed because there was no transcript to assess. And then once I actually got the transcript in, as I'm changing the prompt, sometimes changes to the prompt degrade performance. A change can improve performance. I can go back. And the reason this is all over the place is I'll see where it's going wrong. And I'm working in a training set right now. Test data is not being touched. And I keep changing the prompt to like get the model to go where it should be going. And sometimes fixing one thing breaks 10 other things. And so it's not a negligible task. I've spent weeks doing this, and the end is not very in sight. But it's important to hit a clinically significant threshold. Ours is an F1 score of zero point 0.9, where we can be confident that the majority of the time the model is coming to the same adjudicated decision as a clinician. And we might not hit that for every symptom, and that will be the next paper. Um, so to wrap up, classical machine learning is transparent and explainable, but feature heavy. There's a lot of pre-processing. Large language models, which are the cutting edge, are quite powerful and flexible, but they're quirky, they're less explainable, they're prompt driven, and there are a lot of challenges. Privacy and trust, compute and security. The higher the compute need, the greater risk of data leakage. They can be costly and resource intensive. Um, and interoperability with clinical systems can remain a little undetermined, especially in these black box symptoms. So when you're looking to put natural language processing into your research, you have to frame your problem carefully. You have to build reliable ground truth data, and you have to keep the clinical utility and compliance central to that research design. Um, so with that, if you want to learn more about these studies, we do have some publications on them. In case study one, the full detailed methods of how it was executed. Case study two is actually about the ground truth data, so you're not going to get too much large language model stuff from this case study. It's from the chatbot side, but you're welcome to take a gander. And also, if anyone wants to get in contact, you're more than welcome to reach out to me on LinkedIn, where these papers are also posted. And with that, I will take questions.
Sorry, trying to come off mute. Thank you so much. That was just, I feel like you did such a wonderful job removing the jargon and making this understandable to an audience that me, probably the biggest one here, that would has not done any of this before personally. So thank you so much. I do have a question, and then I'll turn it over, and you folks can just put their questions in the chat. I see some coming in. I when you develop tools like this for clinicians, is what is your understanding of their view? Do they trust them? Are there challenges with getting folks to use these in real world settings when they're developed? Or are they relieved that there's something out there that can facilitate this?
I think it depends on the clinician. So in the motion analysis lab, and I guess in both of these examples, they're very pro. So in the motion analysis lab, we develop machine learning tools all of the time to help with our clinical workflow. And the clinicians are very abreast to it, and there's a lot of vetting to build trust in the systems. And we work with them to ensure that the output is consistent with their expectations of the output. Um, in these cases, these are more classical machine learning approaches that are much more explainable. And then for the dementia project, Drew actually is a clinician who's leading this project. He is fully in on the ability for large language models to reduce workload, but
Mhm.
also the amount of work that goes into being able to have that deployed functionally isn't negligible. And I can't speak for him completely, but I would say he probably wouldn't deploy it in the clinic right now in the way that the motion analysis clinicians are more comfortable deploying traditional machine learning approaches in the clinic. So it really varies. And I was recently at a patient-facing event where this isn't about the clinicians, but the patients
Mhm.
themselves were a little wary of AI coming into their clinical care. And so it's also important to remember the stakeholders too, and how these ideas might be communicated to them because it is also their health. But yeah, so it really
Yeah.
varies.
Excellent. Thank you so much. And I'm gonna just open it up. I know there's some folks in the chat.
Yes, I see one
Um,
question there. Have you tried comparing API GBT versus OSS for data that doesn't need HIPAA compliance? And yes, I have. I've used the API for one of my systematic review studies, so it was published literature, it wasn't clinical data. Um, it was GPT 4.0. I found it much less quirky than GPT OSS. Like I didn't have to do that whole prompting schema to get the JSON output. The API calls were much faster. I was getting back um, analyses of entire papers in seconds, not minutes. But this is where the cost benefit analysis comes in because I have free to me OSS access, whereas running the API for GPT 4.0, this was now like a year and a half ago, the prices have probably changed, on 50 articles cost $200. So my experience with the API, it was much more powerful, it was much faster, but you had to pay a premium to use it. Um, Next, does analyzing text in different languages change the methods for preparing the data? If yes, how so? From traditional approaches, I think it's probably similar. So, like the k-nearest neighbor support vector machine, those models do not inherently know language. You are just giving them a matrix that is a mathematical representation of the text data that's present. It does impact the tools you use. So um, you might we'll go back to that slide. Oh, maybe I don't want to go back to that slide. Um, Too far away. But like the stop words dictionary is in English. And there are some tools that have been developed in multiple languages, and we call them high resource languages like French and Spanish. But then there are low resource languages where a stop word dictionary hasn't necessarily been developed. So those pre-processing steps might be harder to accomplish in a low resource language. And then in terms of large language models, there are large language models that have been developed on multiple languages, but much like the tools for traditional approaches, it's pretty inequitable how well these models perform in English versus other languages. And then what data would you use for the training data? Um, I would counter that is possibly not that simple of a question. It really depends on your data set. If you mean the 80%, 20% split, you can divide it in a couple of ways. So you can it for the case of my fall study. I just randomly divided the data 80%, 20%. And there are Python libraries like sklearn that have built-in functions that will automatically randomly divide your data. And you can put a random seed there so it's reproducible, but you didn't have to make any decisions on how to divide it. But in other projects, sometimes you have to be a little bit more thoughtful about how the data get divided. Like perhaps you don't want to divide by text instance, maybe you want to divide by patient. So in future patient encounters, um, the model is deployable, even though an individual patient might contribute 5 fall events or something like that. But it really depends on your research question. Um, then Gemini and robot search. So I've lightly used Google Gemini. They have a current initiative where you get, I think, free Gemini for a year if you have an EDU address. So I signed up for it because it was free and I didn't love it. So I went back to ChatGPT, which I do pay for subscription for. Um, like it was fine, but I didn't find it to be the most powerful. And I won't lie, I have not heard of robot search, so I apologize about that. Um, and then for case study 2, do you think that the difficult part is to define Alzheimer's disease? I was thinking that after you have a clear definition based on patients' descriptions at interview, then you'd build a stat model to predict the probability that a patient has Alzheimer's disease. So that is one of the end goals of the project. So we interview the patient, um, and the chatbot has been trained to target certain types of information, and that can include cognitive symptoms, motor symptoms. Like if they have a lot of rigidity and they have a lot of slowness of movement, their dementia might actually be like a Lewy body dementia associated with Parkinson's disease and like not an Alzheimer's disease. So we have a whole list of symptoms we're targeting to determine whether they experience the individual symptom. And to my understanding, I am not a neurologist. The diagnosis is from the pattern of symptoms that emerge. So we're looking to create that history of present illness statement that includes all the symptoms and their presence and what the patient has individually experienced, but a clinician could read in a page or two. And then we're going to see whether the clinician can come to a unified understanding of the diagnosis when the LLM has created the HPI versus the HPI created by another clinician. Um, so that diagnostic portion is coming later, but we're hoping would be built off of those individual symptom presentations. Um, then will you be responding to questions submitted during the workshop registration process? I will have to pull them up. It would be,
Olivia's gonna pull them up and she's gonna read them for you. So she'll ask you them one at a time.
okay. Should I finish the last one in the chat maybe?
Yep.
Or,
I think the last comment, was there another one?
oh, it was more of a comment with
Yeah.
diagnosis performance of ChatGPT 4.0. In my experience, the GPT family models are extremely powerful. And I think Azure does have a HIPAA compliant string into GPT models, as does AWS. So you can experiment with them. You just shouldn't be using the like OpenAI website to do that experimentation, but they are extremely powerful, but also very expensive.
Right, so one of the first questions we have from the registration was kind of a question, kind of a comment from Viraj Patel, and they're asking about application for non-English languages.
Mhm. So it is quite limited, again, unfortunately. There are some resources available for French, for Spanish, but um, English is really dominant in this field, and um, there just aren't as many resources. You can look for them, but they require extra vetting.
Absolutely. I can't keep an eye on the chat, so Jessica, chime in if there's something I'm missing. But another question that we have is from Grayson Baxter, and they asked, what, if any, ethical concerns are there around using NLP/LLMs with PHI? How does the use of these tools impact grant application and IRB permissions?
Mhm. So I think I largely covered that. You have to
Yeah.
make sure it's a compliant thing. In terms of grant applications, um, I think as long as you show that you're thinking of those things, that goes a really long way to reviewers. And also by thinking of, is it HIPAA compliant? What are the costs? What infrastructure do I have access to? Like, those are questions you need to answer anyway in grant applications about any type of research you do. And I know a common pitfall, because large language models are so powerful and promising, it's so easy to promise the world in a grant application because hypothetically a large language model would be capable of doing it. But from a resource perspective, you can't drop $20,000 on API compute. And so understanding the exact tools that you'd have access to goes like a really long way in a grant application.
Awesome. Thank you. When I read it out loud, I realized that you covered that largely, but might as well give it some more airtime. The next question is, what are the most promising current applications of NLP in outbreak detection and public health surveillance, and how do you see these methods evolving over the next 5 to 10 years to strengthen real-time epidemic intelligence?
Mhm. So there are a lot of methods that can be done. I'm most familiar with what we do in the Sarker lab, where we use social media as surveillance. So a recent project I was involved in was looking to detect um, social and clinical impacts of opioid misuse based on disclosures on Reddit. And that was the project actually that got the zero point 0.5 F1 score, where we're improving on that named entity recognition task, but it's still nowhere near perfect. Um, but other work in the lab has been very promising, where we were able to kind of detect the rise of fentanyl from Reddit data. So there are a lot of natural language processing approaches that are capable of doing that. And it might surprise you, a lot of these tools were transformers or earlier, not necessarily large language models for surveillance. And I feel like a broken record, but like the best tools are also defined by your own infrastructure and resource availability, because some of these simple tools can be really good at surveillance, even rule-based. If you know what you're looking for, it might not be comprehensive. You might not catch every case, but if you could survey thousands of people with simple rule-based terminology searches on social media to find your target information, that goes a really long way. Um, in terms of where the field will go in 5 to 10 years, I think it's going to be really different in a year. Like the rate of development has been astounding. It's hard to keep your finger on the pulse of the latest large language model. Costs are going down, accessibility is increasing. Going back to GPT OSS, that's a GPT family model we can host locally now, which was unheard of last year. Um, so I think it's very exciting. I think these tools will get stronger, and our ability to like comb through the internet ourselves for our own research surveillance needs will increase. But right now, the tools are um, good, but like there is room for improvement, and it takes a lot of pre-processing to identify your target information, whether it be through keyword search or more advanced embedding models.
Thank you. And then last question we have from the RSVPs. You may have already touched on this as well, but the best tools to conduct analyses. And I think you've already mentioned that it's based on the team and your data, but feel free to take one.
Well, I'll just pitch again. I said this, but I meant it. ML Flow is amazing. And it applies to everything from rule-based pipelines through large language models where you can define your parameters of interest. So, like changes you're making to the model, whether you're changing the number of neighbors or you're changing your prompt, it will record like which data set you use, which data split you used, really any parameter you're changing, you can define in ML Flow, and it keeps it all packaged really nicely so you can see how your experiment progresses. Because it's really easy to one lose sight of the beginning, or and I'm very guilty of this historically, where before I knew of tools like ML Flow, I would train my k-nearest neighbor in one cell of my Jupyter notebook and have its output, and then in the next cell train my next one and then have its output. So I had like thousands of lines of code in one notebook where with ML Flow you can make a loop and for classifier in classifier models apply this and then ML Flow will track the output. So I think that's a really powerful tool, and you can host it online, which you probably don't want to do if you're sharing any data in it. Um, for collaborators, but you can also keep it local on your own machine, and it's all text files, so it doesn't take up a lot of space and it doesn't require really any computational power to use. So it's just a very nice lab notebook. Um, what about any recommendations for existing qualitative analysis software that you don't have to pre-program code? I can't say I'm terribly familiar. A lot of the space I'm in is coding the thematic analyses, um, but I'm sure that they exist. I'm sorry, I don't have one in mind.
Folks are also welcome to come off of mute if you have any questions you would like to ask directly.
Any other questions? Feel free, like Olivia said, come off mute or raise your hand and we'll look for you. But if there are none, please uh, just join me in once again thanking Dr. Powell for her wonderful wealth of knowledge and such an informative presentation. And thank you again for making it something so complex and jargon filled, really digestible for this broad audience here today. And we will make accessible a recording for folks that weren't able to join the whole time or who would like, to go back and get pointers later on. And just feel free. I'm sure Dr. Paul's willing to field other questions later if you'd like to contact her directly. But thank you again so much. We appreciate you taking the time today and just thank you. So.
Thank you so much. We appreciate it.
Yes. Well, thanks everyone for attending, and stay tuned for our next series of workshops. We'll be sharing those and announcing those soon. Thank you all.
Take care, everybody.